back, CHEM200. This is the first lecture after exam 3, and this is officially the home stretch. So that's the good news. The last bit of new material is on its way. The probably more challenging news, this is the biggest chapter. What I mean by biggest, it is the longest, has some really difficult concepts. The homework assignment is the longest, so really encourage you, commit to chapter 9, put in the time, come see me in office hours, let's talk about this. But this is a big chapter. We've got 2 days on this chapter. Exam 3, it'll take me some time to get that back to you. You still have some time to withdraw from the course, but I wanted you to see what's ahead. You've got 2 quizzes remaining. That's May 11th, May 18th. That activity 1, the seminar activity, many of you still have not turned this in. I know some of you went to seminars on campus, and seminars in person. If you didn't, that's fine. You can watch seminars on video, but go look at activity 1 to complete that. I will have emailed you about study session with Charles. There's one more study session to get ready for exam 4 and the final. Speaking of the final, it's an ACS standardized exam. So I encourage you to check out the email about buying an ACS study guide. This might be something that you want to practice and purchase your own study guide. There are many practice exams on a line that we'll go over in practice that are for free, but if you wanted, there is this resource available. Wanted to revisit our class theme. So there's been lots of adjustments this semester, a lot of adversity, but the idea, remember, is we were thinking about how our chemistry class relates to being an Olympian. So I encourage you to revisit your goals. What did you set out in the beginning? And acknowledge things have changed. So maybe your goals need to change. Maybe this last month you need to set some goals. But evaluate what you want to do. And then I really encourage you, this is my big encouragement. I think it makes a huge difference if you finish strong. Okay, so regardless of how things went on campus, remote learning, what you can do in this last month, I think will really make a difference on how you feel about this semester. So really encourage you, finish strong. All right, so what we're going to do in chapter 9 is revisit some terms maybe you've seen, energy, work, heat, and have some good definitions. This is the chapter on thermodynamics or thermochemistry. So we'll talk a lot about what that means, but you're going to see a lot of equations, okay? And some of these equations will be familiar, but there are so many. That's the challenge. Many of these equations are pretty straightforward. You add 2 things, you multiply a couple of things, so the equations in themselves might not be that complicated, but because there's so many, you have to kind of sift through and identify, what do I have, what equation do I need to use? So that'd be here, we'll get another equation, PV work. Look at this, calorimetry, 1's constant volume, that's one set of equation. Calorimetry, constant pressure, that's a different set of equations. So really need to work through that. As I mentioned, you'll have the whole week for chapter 9, so I encourage you to take the time, small pieces at a time, and come to office hours. All right, so this is thermochemistry. And you can see here, this ice is on fire. You can Google and see some videos of money being on fire. So this is kind of this interchange of energy and chemistry, and there can be some really interesting things that can be done here. So let's get started on some definitions. I use this all the time. You use this, I'm sure, a lot. Oh, I don't have the energy today, or I'm full of energy, or I got to go to work. Man, the work was so hard that I was doing. Well, what do those terms mean in chemistry? Okay, so energy is the capacity to do work, and work is really have a specific definition: the result of a force acting over a distance. My job, I record lectures, write out slides. So that's not like moving things. I'm not, working in the garden, or I'm not working in the fields. I'm not building a house. I'm not moving things. But this is what we're talking about for chemistry. Working is a force acting on distance. Pretty common examples of that are the billiard balls here. So you got the energy, the ball in motion, and then it hits the purple ball, and it does work because it moves the purple ball, and now it's energy in motion as well. So energy might be a familiar term, and you can maybe even think about different types of energy that you're familiar with. So you might want to make a list. What types of energy do I know? What are examples of those energy? Some of those, again, are guiding definition, capacity to do work. So kinetic, you've probably seen, that's motion. That's what we just saw before. Thermal energy is the energy associated with temperature. Okay, the temperature of something is identifying like the motion of the particles of that substance. So that's this falling under this kinetic or motion energy. Potential energy. Oh, you have such potential. What does that mean? Well, maybe that's a good thing. Maybe it's a bad thing. Here we're talking about the composition. So what you put in your car, the composition of that has the potential energy to make your car go. Okay, so gasoline has the components to make your car go. If you put water in your car, or if you put something else, it doesn't have the composition to do that. So that's composition. Position, we're going to see how the particles are arranged, or how the atoms are arranged in a molecule. That tells the potential. The chemical energy is associated with the positions of electrons and nuclei. So this is what we've been doing, is structure. What do molecules look like? All those bonding theories that we covered. And now that's the associated with the position. That's this chemical energy. So the chemical energy of kale or the chemical energy of quinoa is different than the chemical energy of, Snickers or something like that. So chemical energy, the position of the electrons and nuclei. So a couple of logistics. If we're talking about energy, we're going to be using specific units. So a joule, capital J, and these are the derived units where it comes from, but really we'll be using it as a joule. Physics, you would definitely want to break it out more, but for the most part we write it as a joule. And maybe you've seen before in Chem 152, but 1 calorie is equal to 4.184 joules. That is a conversion that you'll need to know and use. And then you can look at this and say, wait a minute, I know calories. Well, you do, but not this calorie. The nutrition calorie is capital C. The calorie in chemistry that we're talking about is lowercase c. So it takes 1,000 calories in chemistry to make up 1 calorie in nutrition. I know it's super annoying that it's the same except for that one capitalization. So that's calories, kilocalories, but what we will use is right here. 1 calorie equals 4.184 joules. This is what we'll spend most of our time doing. So we go back to the beginning. This was Chem 152, scientific method, laws, theories, and you saw possibly the conservation of energy, and that states that energy is neither created nor destroyed. So what does this mean about this conversion of energy in chemistry? Well, energy can be changed from one form to another, so that kinetic, potential, back and forth, and can be transferred from one object to another, what we just saw with the billiard balls. So some other terminology that is really critical that I try and really emphasize in my Chem 152 labs, and then also comes back in Chem 200L labs, is perspective. So what we're meaning is what's the system and what's the surroundings, okay? So when describing energy changes, you got to have a reference point, okay? So what we're looking at is the system. That's the object of study. And then everything else is the surroundings, okay? So what I mean by this is if I talk to you and say, hello, would you like to be involved in a $500 transaction? Well, that sounds pretty good, right? Transaction. Well, it's about perspective though. Are you getting the $500 or are you giving the $500? What part of the transaction are you? Are you the system or are you the surroundings? Same thing with energy. Is energy being transferred out of the system or into the system? Transferred out of the surroundings, into the surroundings. So this is the key that we really need to emphasize right away. Any kind of problem, what's going on, what's the system, what's the surroundings. So systems with high potential energy tend to change such that the potential energy is lowered. So this is looking for stability. So I've got a couple of examples of this we can look at. First one, again, billiard balls. We've got gravity And energy transformation, this is our potential energy. It's being held above the table, the gravity pulls it down, and there's a transfer from potential to kinetic. So that's our transfer, energy is conserved, and we can see that here. Next, you see the compressed spring. Okay, so that's potential energy, high potential energy, because it's compressed and it's released, and now the ball goes into the air, into motion. That's the kinetic energy. So that's another energy transformation. So now let's look at this in terms of system and surroundings. So before the energy transfer, we have this system energy gauge, and we have a surroundings energy gauge. Okay, so we got a quarter of a tank here, we got half a tank here. So you can see that the system loses a quarter of a tank. So that's that transaction I was mentioning earlier. So if the system loses it, that's got to go somewhere. It just can't disappear. Remember, energy is conserved. That goes here, it gains a quarter. So now the surroundings is up to half. So this is key. The exact amount is transferred. That's the conservation of energy law. So that takes us to first law of thermodynamics then. Okay, thermodynamics is the interconversion of energy. Chemistry, the first law of thermodynamics is that energy cannot be created or destroyed. So we just saw that on the slide before. It can be transferred, but it's conserved. So the total energy of the universe is constant. So this is fun for chemists to talk about universe. We don't use that terminology too much, but in thermodynamics you definitely do. But this is really what we're about in this chapter. It's transferring. What's happening to the energy? Is it being lost? Is it being gained? How much? And so on. So let's get started with some of these equations. Okay. So what we've been talking about is the total energy of the universe is constant. So that means the change in energy of the universe is zero. Okay. And we've said, well, the system and the surroundings, energy is conserved, so that is zero. Okay, so that's two equations there already on the list. Okay, two equations. Surroundings, energy of the surroundings plus the energy of the system equals zero. Change in energy of the universe equals zero. What does this change mean? Well, you've seen change before, delta T. We'll see delta V in here. So the change in energy is the energy of the final minus the energy of the initial. So that's another equation. So we've got three right here. Well, take a look. We want to know how the system and surroundings are related. They're opposite of each other. So you can look at this as a fourth equation, 2, 3, 4, or you can say, wait a minute, this is one of my equations, and I just rearrange this, subtract E surroundings goes over here, so negative E surroundings, delta E system. So you may want to memorize a whole library of equations, or you may want to know a few and then derive the other ones. Okay, so some terminology that you need for these equations. One is that is a state function. Okay, so a state function is change in altitude depends only on the difference between the initial and the final values. Remember we said E final minus E initial. It does not depend on the path taken. So if you take a look here, you go from 0 to 10,000 feet, you made it to the top. That's a change in altitude. That's a state function. However, the distance is not a state function. Okay, if you took the distance up the face, a lot harder climb, but it's 5 miles. If you took the nice meandering walk up, that's 12 miles. Okay, see, those are different. However, the altitude, the change that both of those underwent was the same, 10,000. So change, altitude, that's a state function. That's what we're looking here in thermodynamics, state functions. So let's look at the chemistry then. So this is energy we've been talking about, or it can be labeled here as internal energy. And we see that we have the reactants, carbon, oxygen at a higher energy. You see the y-axis, that's at a higher energy than the product, carbon dioxide. So if it moves from here to here, what's going to happen with the energy? Okay, what's going to happen with this change? So the reactants going to the product, you can see that the energy flow is going out of the system to the surroundings. So that means the change in internal energy of the system is negative, it lost, and the change in the surroundings is that same number positive, that's gained. So the opposite can happen too. If you go the opposite direction, you start with carbon dioxide, lower energy here, you go up. That means that it had to take energy for it to go from reactant to products. So the change in internal energy is positive, that goes up, and change in the surroundings is negative. So this is what you've seen before probably in Chem 152, endothermic and exothermic. So an endothermic is positive, takes energy, goes up, and exothermic is negative, it gives off energy, and it goes down. So that's this system, surroundings, gaining, losing. So now we talk a little bit more about internal energy. So adding another equation. This equation is the internal energy is equal to the heat plus work. So again, this isn't complicated. You just add these two together. But what the complicated piece is, wait a minute, is this heat positive? Is it negative? Is the work positive? Is it negative? So let's take a look here. Heat in this table, if the system gains thermal energy, okay, if it gains heat, that's a positive change. Okay, if it loses, if it cools, that's a negative change. If the system has work done on it, that's a positive. Okay, so I know that sounds kind of strange. Well, the work was done on the system. We'll explain that a little bit more later, but this makes sense, right? If you do work, you lose energy, so that's this negative work done by the system. So then overall, we see these are additive, heat plus work. Overall, if it's positive, energy flows into the system. If it's negative, energy is going out of the system. So let's look at some of these concepts. So take a look here. Which of these changes always results in an increase in the internal? So the key here is always results in an increase in the internal energy. So go ahead and pause, look through this, come up with an answer. What I want you to see here is if we have a system absorb heat, you want to think about the sign. Okay, so absorb heat does work on the surroundings. So absorb, positive, but it's doing work, negative. The system releases heat, negative, and does work, negative. The system absorbs heat, so that's positive, and has work done on it by the surroundings. This is positive. So up here, if we had a positive and negative, it depends on the magnitude. Is the positive bigger or is the negative bigger? Here, this is always going to be negative. Here, this is always going to be positive, and that's the question. What is it going to be? Here, if we have releases heat, negative, and has work done on it by the surroundings, positive, so that depends on the magnitude as well. So we can see C is the only one that will definitely be positive. So that's conceptual, understanding how do we rationalize this equation. And remember, the equation is delta E equals Q plus W. Okay, so now let's do the quantitative piece. Okay, same equation. Here, Q, W, those equal internal energy. So really, what we need is the sign. Okay, so if it's for a system that does 422 joules of work and loses 227, so the key here, if it's doing, that's negative. If it loses, that's negative. And remember, these are just additive. So if those terms are changed at all, for a system that has work done on it, changes the sign. For work that gains, changes the sign. So you can see here, additive, put in the negative signs, and you get that is the total internal energy change here. So this is how the relationship between heat and work. Okay, so to summarize this, remember Q is heat, W is work. If Q is greater than 0, it gains heat. That means if it's less than 0, it loses heat. And we can also know this about work, really emphasizing, is it done on the system or by the system? So we already made a table like this on that previous conceptual question, but really want to emphasize, if it's positive, positive, internal energy is always positive. If the heat's negative, the work's negative, the internal energy is always negative. If there's some combination of signs, that depends on the magnitude. So whichever one is bigger leads to the sign. Okay, so let's think now about some Chem 152L chemistry, some Chem 152 concept chemistry. So a piece of metal, 85 degrees, is added to water at 25. The final temperature of both is 30. Which of the following is true? So I encourage you to think about this, pause, look through, come up with an answer here. Really, this is saying conservation of energy. Okay, so the heat lost by the metal, heat gained by the metal, no. Heat gained by the metal, heat lost by the metal, no. If we're having a transfer of heat, that has got to be equal to each other. So conservation of energy, that's being transferred, it's not being lost or gained. So heat is something you've seen possibly before in previous chemistry. So now we're going to go and talk about some familiar ways to calculate heat, maybe, and then some definitely brand new ways for heat. So heat is the exchange of thermal energy, we mentioned that earlier, and a temperature difference is what governs this. So the slide before, that hot metal, putting it in the room temperature water, that temperature difference then resulted in this transfer of that thermal energy. So a couple of terms, the heat capacity, capital C, is the amount of heat required to raise the temperature by 1 degree Celsius. So that's joule per degrees Celsius. This might sound really familiar to something that you know, but I want to emphasize that this is just joules per degree Celsius. That's the units. So the heat then, Q equals C delta T. What may sound really familiar is the specific heat capacity. I know these are very similar. This uses CS, and this uses C in this textbook. Now it's the amount of heat required for 1 gram. Okay, so that's the difference. So you can see the units now are joules per gram degrees Celsius. So that's the Q equals MC delta T, maybe you're familiar with. So this is what we'll follow up on, but you can see two more equations right here. Q equals C delta T, Q equals MC delta T. So the next piece is a conceptual question. There's no calculations. However, that's a Q equals MC delta T problem. Okay, so if we look at this, what's being asked is which would require more heat, that's a Q question, to raise the temperature by 1 degree Celsius, a cup of water or a swimming pool. So of course you have so much more mass to raise, that's the swimming pool. So again, which would require, so this is not a calculation even though there's numbers here, but this is a Q equals MC delta T problem. So Q equals MC delta T, and if you look, which would require more heat, so again we're looking at Q, to raise the temperature by 1 degree Celsius. Okay, so if we look here, we're having our delta T is the same, and our mass is the same. So the question is relationship of C and Q. So in this case, which would require more heat? So the larger C, water requires a lot more heat than gold to raise it by 1 degree Celsius. So this is very beneficial for us. Our body temperatures, mostly water, remain at a very constant temperature because of this C of water. And you can see that's where that conversion comes from from calories to joules. So you use this in Chem 152L, identifying an unknown element. So this was a cube. You identified the unknown metal. This is similar. You'll be doing in Chem 200L. So this is an intensive property. If you look up, see the specific heat capacity, then it doesn't matter how much you have of it, you can identify it. It's 0.385, that's copper. 0.449, that's iron. You can see these two very close, but then you can use other factors. What does it look like? So let's do some problems with this. Okay, so again, remember there's a host of equations already. So part of it is just starting with the equation. So calculate the amount of heat released when 7.40 grams of water cools 49 to 29, and then the specific heat here is given of 4.18. So you can look, think about your equations. If you're given a C and the units are joules per gram degrees Celsius, that's a Q equals MC delta T problem. You have the M, you have the C, and now you've got the delta T. So plug it in and you can solve for Q. Now we see negative 620 joules. That's really emphasizing, remember that negative sign tells us this is exothermic, heat is being released. So that was very introductory Chem 152 problem. Then you stepped it up in Chem 152L and you saw, well, you've got metal at a hot temperature, and then you got a calorimeter. This would be very familiar if you took lab at Miramar. You got a mass of water, room temperature, and then their final temperature. So remember the system and surroundings here. We've got a metal, that's the system. It's releasing heat to the surroundings. That means the Q of the metal and the Q of the water are opposite of each other. So Q metal minus Q water. Well, Q, we just said, is MC delta T. So this is MC delta T equals minus MC delta T. You've got everything but the specific heat of the metal. So now you can solve for that as long as they're in the correct units. So go for it. Most common is leaving off this negative, so make sure really emphasize the Q of the metal is opposite of the Q of the water. That's that energy is conserved. MC delta T minus MC delta T, and you just now got to keep track. That's the mass of the metal. This is the mass of the water. This is the specific heat of the water. We're looking for the specific heat of the metal. The water or the metal went from a hot temperature to then that a little bit higher than room temperature, and the water was raised to that 35 temperature. So solve this, you get a number, and then look on the table that I provided on the previous slide, and then you can identify that that's copper. So that's heat chemistry, stuff you've seen before. Q equals MC delta T, Q equals negative Q. So several equations we've put in, but my hope is that that is familiar. Okay, so now we're adding some more pieces to this and adding some more equations, of course. So we said internal energy is heat plus work. Now we're going to talk specifically about a certain type of work, and this work is pressure volume work. Okay, so remember our internal energy is heat plus work. Now we're saying, well, we can substitute in that equation work equals minus P delta V. Okay, and this is this diagram showing you what this means, like in a combustion engine, the change in the volume of the piston. This is where this comes from. The main takeaway for us is pressure, it's constant pressure, times a change in volume. Okay, so you can see the units of that are pressure, atmospheres, and volume liters for the work. Well, this equation does not use those units. It uses the units of joule, so we have to do this conversion. 1 liter atmosphere converts to 101.3 joules. So this is a work conversion, changing the units here. So this problem here I put it in because it's a good summary, but it's exhausting. There's a lot going on here, okay? So first I want to read this and work through some of this together. This is how I would do this problem actually on campus as well, is more of a let's do it together than just show you this and say go for it, because I've done that many times and it can be very painful. So let's look through this. Certain process results in a gas system releasing 68.3 kilojoules of energy. During the process, 15.8 kilocalories of heat is released by the system. Okay, so what we just said is energy. So we got to translate that into an equation. And we said heat, so that's the energy equals heat and work. Okay, that's what we just got from this first two sentences. If the external pressure is kept constant at 1 atmosphere and the initial volume, so wait a minute, that's pressure and volume. So this takes us to our other equation. Work equals minus pressure delta V. Okay, so these are our two equations, but let's take a look. Actually, we have energy in kilojoules, so that's a conversion. That needs to be in joules. We also have kilocalories. That's a conversion. That needs to be in joules. And remember this atmosphere liter pressure. This is the conversion. That needs to be in joules. Okay, so it's really two equations and several conversions. Okay, so this is the problem. Why put this in here is a refresher of all of these conversions. What needs to be done in order to use these pretty simple equations. Okay, so all the work's coming at once here, so it can be a little overwhelming, but I want to go through this. This is the equation we started with. Internal energy is the heat plus work. So I said that's kilocalories. Well, we need to get to joules, so that's calories. That's the conversion to joules. So now we're in joules. Okay, that's the internal energy. So that's delta E, internal energy. You were given that's the internal energy here, the 68.3 kilojoules of energy. That's internal energy. What we just converted up here, the 15.8 kilocalories, if you recall, is up here. That's the heat. So now that the heat is in joules, the internal energy is in joules, we can just subtract these and get the work in joules. Okay, well, this is PV work, so this is our next equation. Remember, PV work is not in joules, so we have to convert that using this conversion factor, atmosphere liter to the 101.3, which I think sounds like a radio station. 101.3 joules right here converts that to this work. I know this is strange, but that's the units of work. It's just in pressure volume work. So now we can see that our equation, go back up here, negative P times delta V. So the pressure was 1, and the delta V, we have the initial volume, and we have what it's equal to. Okay, so that's the work and pressure volume units right there. That's the pressure, and this is the volume. Rearrange this, and we get a volume of 32.3 liters. So this is a very exhausting problem, but what the highlights, this is 1, 2 equations, and then we had 1, 2, 3 conversions. Okay, so there's a lot that can happen in this chapter. All right, so that takes us to calorimetry, and I get nervous when we get to this point because, oh, calorimetry, I've done calorimetry. Well, it's very unlikely that you've done constant volume calorimetry, okay? So this is different. So let's see how it's derived. We've talked about heat equations, MC delta T. We've talked about work equation, delta P, negative P delta V. So what we're now talking about is the internal energy is the heat plus the work, and this subscript V is at constant volume. Wait a minute, constant volume. So if we have no change in volume, then we have no work. Okay, so if we have no work, then the internal energy of the reaction is equal to the heat at constant volume. Okay, so that's what this calorimetry is used for, is to look at situations where the volume is constant and we get the heat in those conditions. This is called a bomb calorimeter, and it's a very sealed reaction vessel here, surrounded by water, the thermometer in the water, and the reaction takes place down here, and this is tightly sealed because when a reaction happens, it gives off a lot of heat and then increases the temperature of the water. So we're talking about combustion reactions. Okay, this leads to a new heat calculation. Okay, because we're not basing it on the mass of the surroundings. This is typically, Q equals mc delta T is the mass of the surroundings. But here what we're doing is that this is a whole system, this calorimeter. So the calorimeter system has a constant, C cal. That's going to change temperatures. That tells us the heat of the calorimeter. Okay, so we got the heat of the calorimeter, but really what we're interested in is the heat of the reaction. Remember, those are conserved, those are opposite of each other. Okay, so this is very similar to the Q equals mc delta T, Q equals mc delta T, and then you set them up equal to each other. So in this case, Q of the calorimeter is the opposite of the Q of the reaction. So let's take a look at one of these problems. Again, we kind of have to sift through what we've got here. We've got grams of a substance, molar mass, so we can definitely go to moles from there. That's a nice step. And that's in the bomb calorimeter. Okay, so we go from 20 degrees Celsius, and that gives us the constant of the calorimeter, and that's kilojoules per degree Celsius. Remember, that tells us the equation right there. If we see kilojoules per degree Celsius, what I'm saying is that this is a Q equals C delta T problem. The reason we know this is because heat is in joules, and then if we look, whether it's kilojoules or joules, it's energy per degree C is the constant, so the only other piece on this side of the equation is the delta T, which is in change degrees Celsius. All right, so the internal energy for the reaction is negative 3.23 times 10 to the third. What does that tell us? Well, that tells us negative, it's exothermic, it's giving off heat, so my calculations better go to a temperature that's higher than 20.27. Okay, and that's what we're solving for. What's the final temperature? So a roadmap here to think about is if this is kilojoules per mole, this is turned into moles, that gets us to kilojoules. That gets us to kilojoules of the reaction, which is opposite of the kilojoules of the calorimeter, and then that gets us to Q equals C delta T. So go ahead and give this a shot, and then we'll talk about it here. So all of it's coming at you, but what I wanted to emphasize, the equation Q equals C delta T, that's one equation, and then Q cal, remember, is equal to the negative Q of the reaction. So how do we get the Q of the reaction? We convert grams to moles, here, this first one, and then we do kilojoules per mole times moles. That gives us the Q of the reaction. Okay, so again, negative, that's going to give off. So the Q of the calorimeter then, you can see here, is positive. And since this is in kilojoules and our constant was in kilojoules, we can just keep them in kilojoules. They just have to be in the same units, whether it's joules or kilojoules, doesn't matter. Just has to be the same units. So that's our equation, Q equals C delta T. That's getting us to our final answer. We've got our delta T, we've got our C, and we've got our Q. Solve, and like we said, it's exothermic reaction. It is higher than 20.27 degrees Celsius. So that's constant volume calorimetry. Next, what we're going to talk about is enthalpy, and maybe you recall this from Chem 152, but in my classes I focus on this very little, but it's the delta H. That's the variable for enthalpy. So enthalpy is the sum of its internal energy and product of the pressure and volume. This is kind of a confusing equation here, but we've said internal energy, we've talked about that. We said pressure and volume is work, so now we're adding another work term here. So this is delta H, enthalpy. Okay, well, it's a state function. We've been talking about those. That's pathway independent. And really, I stress this is the heat or enthalpy at constant pressure. Okay, so what does this mean? Well, if you've got internal energy plus pressure times change in volume, now we can break out and say, wait a minute, internal energy we know is Q plus W. And you see here the subscript, heat at constant pressure. So enthalpy is heat at constant pressure plus the work. Wait a minute, work is the opposite of P delta V. Remember, work is negative P delta V. So that's work and the opposite of work. So what we actually have is enthalpy is the heat at constant pressure. So this is a different derivation than before. We had constant volume, now we've got constant pressure. So this is enthalpy, and enthalpy is used significantly in Chem 201 as well. So this is a really important groundwork chapter leading to Chem 201. So I've already been using these terms, but now we can see it right away. Enthalpy is delta H greater than 0, so that's positive, endothermic. That's heat absorbed. We can just even consider heat as a reactant in that case. So when you see now delta H positive 181 kilojoules, you can imagine that heat is over here because it's a reactant. It's being absorbed. Okay? Exothermic, negative, it's released. It's a product, so you can even just write in heat. Exothermic. Okay, so that's endothermic, exothermic. Let's take a look at some concept questions based on this. So if you take a look at here, which of the following has a negative value? So that should be telling us which of the following is exothermic value for enthalpy. Go for it. So I want to go through these. The combustion of gasoline, you may know in your car, that definitely gives off heat. So that'd be a negative value. The melting of snow, okay, so what does that mean? Going from melting, that's solid, to liquid, that actually takes heat, right? It takes the sun to come out. I mean, this doesn't apply to us, of course, but then, you know, up north, we got to melt the snow, solid to liquid. The evaporation of ethanol, that's liquid to gas. So again, to get the particles from the liquid to the gas state, that takes heat to separate the particles. Sublimation, that's a solid to the gas. So again, all of these are endothermic. Combustion, negative value, we would write the heat as a product. So that's exothermic. So in Chem 152, you might have talked about some of these things. And this is where I covered in my classes was just a little bit of stoichiometry. Okay, so if you have a balanced chemical equation, so this is propane, you've got 1 propane, 5 oxygens, 3 CO2s, 4 waters, and it gives off negative 2044 kilojoules. Well, so now you can draw stoichiometry and say, actually, for every 1 mole, that's negative 2000 kilojoules. For every 5 moles, so these are just mole ratios with the enthalpy term. That means these are conversion factors then. If you have grams of propane, you can go to moles of propane. And then this is the big one. The mole ratio now involves the kilojoules. That comes from that term right there. So this is enthalpy. Remember, enthalpy is constant pressure. So there's calorimetry for this. And guess what? You've done this calorimetry most likely. This is constant pressure calorimetry, and this measures the enthalpy of the reaction. Okay, so this may look really familiar. Coffee cup calorimeter, you're stirring it, You've got a thermometer. That's our MC delta T. Okay, that's Q equals minus Q, and that's Q. Now the Q of the reaction is telling us, because it's constant pressure, that's delta H, or enthalpy, because enthalpy is at constant pressure. So these problems, I would say, are a little step up from Chem 152, but they're still related to this constant pressure calorimetry. So take a look here. Questions asking for final temperature, that's delta T, TF minus T initial, so we can get final temperature. But take a look at this. We have a 50 mil sample of HCl. We have 50 mil sample of sodium hydroxide, so there's going to be a reaction. The initial temperature is 19 degrees, 0.5, and the enthalpy of the reaction is negative. So again, that means this is going up. This has got to be higher than 19.5. And look at this. This is kilojoules per mole. I can't emphasize enough, sodium hydroxide. That means we need moles of sodium hydroxide. I know we've got other stuff, but we need moles of sodium hydroxide. A couple other things. Assume the density of the solution is 1 gram per mil, and then the specific heat is 4.18. So go for it. Calculate here the final temperature. So what you can see is our Q of the reaction is the enthalpy of the reaction. And remember, the constant that was given is negative 57.2 kilojoules per 1 mole of sodium hydroxide. So that was the enthalpy of the reaction. So we needed to multiply that by moles. Well, you had molarity, so this is solution chemistry, moles per liter. You had the liters, that gives you moles times kilojoules per mole. That gets you kilojoules, then joules. Okay, so that's a little work there. Chem 200 though, that's solution chemistry and enthalpy, kilojoules per mole. So we got now joules, and remember Q of the reaction is opposite of the Q here. So we go and we need mass. Well, if you need the mass of the solution, you got mils, no problem. You got density, you got 100 grams, okay? So now you can see we've got the Q equals the negative Q, so this is negative 100 C, and then the delta T. So I've kept the delta T here and saving the final minus initial for last. Delta T, you can see it gains in temperature, 1.71 degrees Celsius, and that means that this was definitely an exothermic reaction, and we had an overall final temperature of 21.21. So this is the first part of chapter 9, a lot of equations, a lot of concepts. Now we're going to continue to apply this enthalpy in part 2. Come see me if you want to talk about this in office hours.